but it should work out nonetheless. So I just started the recording. So is this the equation that you ended up with, Elizabeth? You didn't use the quadratics? All right, so this is equal to 0. All right, so if you did, you can see there's a small difference in the percentage between using the quadratic and not. So if you solve through, the other option would have been that you could have just simply, assumed that minus x was very small, and then eliminated that and then solved for the percentage. And you can see there's two different answers. They're both really close to one another, probably within experimental error. Right, so once you get to this point, you then plug into the quadratic equation, which I am. Right, so you end up with, I'm not going to solve all of this, right, but you end up with x equals minus 1.5 times 10 to the minus fifth plus or minus square root of 1.5 times 10 to the minus fifth squared minus 4 times 1 times 1.5 times 10 to the minus 8, all divided by 2. And then you solve for x, and I don't have, that's where I was having calculator errors, so I don't know what the answer to that was. And once you solve for x, I'm not going to go through this and belabor the point because we've done this before. All right, once you solve for x, you're simply going to plug it in to the equation here, right? Once you have x, you plug into the equation here. So we plug in here, and you solve, you get the two different concentrations. And then you take the one that makes the most sense and plug it into the pH equation. Or actually, you don't even need to do that because you're doing percent ionization. You can just simply plug it into the equation down below. All right. That problem was a lot longer than I expected it to be. All right. The next problem asks for the pH of 0.028 molar solution of ascorbic acid or vitamin C. And it says see table 16.3 for the Ka1, Ka2. Right. So the first thing you need to do, if you remember yesterday when we were talking about polyprotic acids, right? Polyprotic acids, if you need Ka, it has to be 10 to the 3 or greater difference, then it's no longer going to have an effect on, if the first and second are no longer going to have an effect. So if we're looking at this problem, when we worked through the problem in class, right? We had this problem here. We're looking at carbonic acid, and they were, we had worked through and the carbonic acid down here, and you can see that there's a larger than 10 to the 3 difference in Kas, so the Ka1 is the only one that's going to affect the pH of the solution. So if we look at our sample problem, So you look at our sample problem here, and we have our sample problem, and we're asked the question. We have a 0.28 molar solution of ascorbic acid, and we need to figure out what the pH is. So we look at ascorbic acid on the chart here. We can see the Ka1 and the Ka2. And you can see there's a larger than a 10 to the 3 difference, so only the Ka1 is going to affect pH, right? So everyone take a couple minutes and calculate through the pH. Good practice with ice tables. Everybody having thorough fun yet with their ice tables? The goal is to get you so used to ice tables that you dream about them, maybe have nightmares. Anyone have any questions along the way? Once you get your answer, A, B, C, D, or E, please type it in the text box. Tell me what you've got. This might be the easy way to go. See if we get a consensus. So right now, Freddie's freaking out because he's the only C. Sorry, Freddie, I'm putting you on the spot. Is anybody else going to be bold enough to end up with the same number as Freddie, or a different one? Or is everyone else still sleeping and in their PJs and drinking a cup of coffee and hasn't worked through the problem? No coffee yet, Annie. You're gonna drink green tea. Once you get old, coffee affects you more. I don't know if it's a good thing or a bad thing. I used to drink massive quantities of caffeine. Sophia, you were born with a cup of coffee in your hand. You show up to class every day. Anyway, all right, let's work through this problem. All right, so you set up your ice table. You have your, call it vitamin C. Then you have your H+, and you have your vitamin C anion. Set up the ice table, simply plugging in, right, 0.28, 0, 0, minus x plus x. And you simply set up your table where you have your Ka is equal to x squared all over 0.28, and we'll assume that the minus x is small, so we'll ignore minus x, and we'll set that equal to, what is it, 8.0 times 10 to the minus fifth. So then after you solve for x, you end up with x is equal to 4.7 times 10 to the minus 3. And you just figure out, if you take, right, 0.28 times 5%, get the, what did I get for the math for that? You end up with a 0.014. So you can see that 0.014 and x is smaller than 0.014. So you can make the assumption here, and we simply then plug this into the pH equation, right, where the pH is equal to minus the log of 4.7 times 10 to the minus 3, which gives us a pH of 2.32. All right. Any questions on that problem? Everyone's still awake. Right. Back to the presentation. This is the part of the class that it's a little more difficult to pay attention to. You got 2.33. Why did you get 2.33? I guess it is 2.33 is the correct answer. I don't know, this was just a copy paste out of the text, so 2.32 is what they got. You are correct, it is though 2.33 on my calculator as well. Would it matter on the exam? Possibly. Depends on the problem. He's got to do the proper rounding. If you show your work, it's really useful. That's why it's going to be useful for all of us to, for you to go through the practice exam, and that gives me a good opportunity. As of last night, when I went off to bed, many of you had not yet worked through the practice exam. A few of you have. And by the way, Brian, yes, I did watch your video. Actually, interestingly enough, I skipped through just to see what the videos were like. I was just curious. And I just happened to stop right when your roommates or whoever they were asking if it made the statement along the lines of whether or not I was going to, whether or not I would see your video. So it was rather amusing on my part. Yes, Annie, I saw your video too. You look rather relaxed. Hey, there's the video for you. So please, everyone, you need to check. If you haven't tested, make sure your computer is working. Make sure you're able to record all your local surroundings. You need to make sure you take the time when it asks you to record the area around yourself. Most of you actually didn't really take the time to properly record the area around yourself, so please do. And because you want to make sure that you're using everything properly. You're going to need your calculators, obviously. So you want to have your calculator sitting on your desk, not your phone, but your calculator sitting there on your desk, so that I can see that you're using a calculator and not your phone for your calculations. There is a calculator built into the program. I'm willing to let you use a regular calculator instead of the other one, but you need to make sure that you properly use the camera to record your surroundings in order for me to see that. Hopefully that's fair enough. All right, let's get back to presentation. Anybody have any other questions about, did anybody have any trouble with the practice exam? I never posted the show your work page yet. I will for the exam. Sorry. For the show your work page, I'll have one set up properly just for the exam. That way I'll be able to have, it'll be easier for me to grade. You can imagine it'll be a little chaotic if I have, because I usually grade one page at a time for everybody's exam. So I go through one problem or one page worth of problems. And it'll be a lot easier for me if everybody has their work on the same page. So that way I can just flip through each one. It allows me to stay neutral in regards to grading. That way I can just, other than the first page, which will have your name on it, the remaining pages will all be blank, because I'll probably print them out for my own sake. Or I might try to grade them online. We'll see. It might be online, but it might be in paper. See how it works out. Yes, the review session for the exam is tonight. Still scheduled. I can't remember what time we scheduled it for. I have to look at my calendar. 7 p.m. tonight. All right. So let's talk a little bit about weak bases. We have about 10 minutes or so we can cover some weak bases. And when we're talking about weak bases, ammonia is probably one of the more common weak bases that we encounter in our daily lives, as a cleaning agent, but it's also used a lot in chemistry. And so like weak acids, weak bases have an equilibrium constant called the Base-Dissociation Constant. And equilibrium calculations work the same as for acids, using the Base-Dissociation Constant instead. And many bases contain nitrogen as an element due to the lone pair. And organic derivatives of ammonia are called amines. So what they're talking about is we have ammonia, NH3, right? So if you draw NH3. You can see there's this lone pair that is present on ammonia. The lone pair that's present on ammonia is the basic function that's present on in the ammonia molecule. It's no different than when we looked at water, right? We talked about a water molecule, right? Water has two separate lone pairs. Remember, when we react water, when this reacts with the proton, right, or another water molecule, we end up with the hydronium ion, H3O+. Right, so this whole substance is positively charged. Right, so ammonia's lone pair is going to act in the exact same way as the water lone pair. So any type of nitrogen-based substance has this lone pair available to it. Well, most of the nitrogen-based substances have these lone pairs available to them to act like bases. So you can see down in the equation down below where we have ammonia is going to react with water just the exact same way that water reacts with itself, but instead now we end up with the ammonium ion, right? The ammonium ion, NH4, is going to look like this. This is at the top. I'll draw it out. Right. You can see the difference between ammonia and ammonium is the one proton is now has reacted with the lone pair on the nitrogen, and the you end up with the same hydroxide as a counterion, right? You could just as easily have imagined this being another water molecule here going to H3O+. So you can see the difference between the two. Don't overthink what's going on here. It's the exact same type of reaction. The only difference is now we have our, instead of the hydronium, we have an ammonium ion in our Kb equation and a hydroxide. And you can see the Kb equation is only given, doesn't look very different than a Ka equation, does it? The only difference between the two is the Kb just refers to the fact that we're starting with a base, and whereas the Ka refers to the fact that we're starting with an acid. Right, so if we, the overall equation is exactly the same way. The way you draw the Kb is the exact same way you draw the Ka. So when we're talking about bases, there are two types of weak bases. Their categories are neutral substances with an atom that has a non-bonding pair of electrons that can accept protons, like ammonia and the amines. And then you have anions of weak acids, which are their conjugate bases. So if we let's look at ammonia right here, right, we have NH3, and you can see, right, there's going to be a lone pair sitting on top of the nitrogen here, or methylamine, right, where this nitrogen again has the lone pair present. Hydroxylamine, the same exact thing. There are lone pairs, and the lone pairs on each of these are going to act as the bases in this reaction. They're, in all the cases, they're just going to end up protonated, right? So obviously ammonia becomes NH4 with a plus charge. Methylamine will become CH3 NH3 with a plus charge. And hydroxylamine will become NH3OH, again with a overall plus charge on the molecule. So you can see that in all of these cases, the ammonia, the nitrogen atom is picking up the proton from in the case of dissolving in water, right? It's always going to be picking up one of the protons off of the water atom there, right? And the reason they're calling them weak bases is if you think about what's going on in this particular reaction is when we have this reaction moving forward, right? What do we produce? Out in the end, we're going to produce the hydroxide ion. And the hydroxide ion, we've all learned that the hydroxide ion is actually a base. So all of these solutions of nitrogen-based compounds are going to produce small quantities to large quantities of hydroxide ions in solution. And these hydroxide ions act as bases. The other group that they were talking about, were anions of weak acids, right? So if you think of a weak acid, you have let me think of a weak acid that we can draw easily. We've talked a lot about acetic acid, right? So the CH3, COH, and we have the conjugate base of that is CH3. Oops. CO minus. So this conjugate base here is going to be another type of weak base. It's going to have a similar reaction, right? You just basically have the reaction going in the reverse direction. It'll look just like the reaction up above. So instead of ammonia, you're going to have the acetate anion reacting with water. It will form, acetic acid, right? So we have CH3COO minus reacting with water, and it will be in equilibrium, forming CH3COOH plus hydroxide. So you can see the reaction is just the reverse, where we're basically always forming small quantities of hydroxide ion in solution when you dissolve the conjugate base. All right, here's some examples of weak bases. Right, we have ammonia. Right, it has a Kb of 1.8 times 10 to the minus 5. We have pyridine. It looks just like the benzene molecule. The only difference is now with pyridine, we have this nitrogen with a lone pair present, and it ends up with a Kb of 1.7 times 10 to the minus 9. So just as with Ka, the smaller the number, the larger the number, the stronger the base. So you can see, we're at 10 to the minus 5th for ammonia versus 10 to the minus 9th for pyridine. So you can see that the ammonia is going to be a much stronger base than pyridine. And let me just draw the structure of the conjugate acid of pyridine. Okay, so that's the conjugate acid of pyridine is right here. You can see you basically have protonated the nitrogen and in the reaction. And you can see last this hydroxylamine, and hydroxylamine is also, so simply from swapping a hydrogen for a hydroxide, oops, that keeps happening here. So swapping a hydrogen for a hydroxide, we have a dramatic loss in basicity. And if you think about what this means, if we have this nitrogen-oxygen bond, right, the nitrogen-oxygen bond has a dipole. Right? There's a dipole that exists between the nitrogen and the oxygen, where the oxygen atom is removing electrons away from the nitrogen. So we have this dipole. Everybody remembers dipoles, right? So they're pulling electrons away from the nitrogen, so that therefore the electron density of that lone pair is less. So since there's less electron density of the lone pair, you end up with a weaker base. Does that make sense? All right. Here are a couple other examples. You can see methylamine. If we compare methylamine, now we have a CH3. I'm going to go back one slide quick. Right, versus the hydrogen of ammonia. We're at 10 to the minus 5 for ammonia, whereas now we're at 10 to the minus 4 for methylamine. So on the differences here is now the dipole goes in the opposite direction. Oops. The dipole goes in the opposite direction here. But now the dipole is pointing towards the nitrogen, so the carbon atom is actually donating electrons towards nitrogen, and it makes it more basic. So we end up with a stronger base, when we have methylamine. The hydrosulfide ion, right? So we're talking about an actual lone pair that has a negative charge on it. It's going to be a weak base, right? The carbonate ion, again, we talked about carbonate. We have actually, it has two different KBs because it has the ability to act as a base twice, right? The hypochlorite ion, right? We have a lone pair that gives us a negative charge. You can see the basicities of each of these, where the carbonate is probably one of the stronger ones, similar to methylamine, whereas the hydrosulfide and the hypochlorite are actually weak bases. All right. So we'll work through a KB example in our next class. I'll see all of you this evening who are going to be able to come to the help session, and we'll discuss problems. So come with questions. Let's see, you have a question. Yes, you'll be given all the necessary Kas and Kbs for any exam that you're going to be taking. It may be charged, it may not be charged. It depends on the problems. Whenever you need, unless you're being asked to calculate a Ka or Kb, you're going to have that. Obviously, this is not on to, the exam this week, but okay. Other questions? Don't forget, send me an email if you're thinking about changing your day. Again, I think most of you, if you may be traveling this weekend, but just let me know. I'm going to leave it open. No more questions? Then we'll talk to you later. Hope everything's going well. Thanks. Thanks, everybody.